My name is Chad Williams, and today we're going to talk about independent samples one-way ANOVAs. The first thing we want to do is we want to start off by creating a data frame, but I'm going to do this in a few different steps here. So what we want is we're going to have an independent variable with 3 different levels, and so we're going to make 3 different normal distributions. So I'm going to concatenate these distributions. So I'm going to start off by saying our norm, and let's say 50 data points per level. And then we're going to have, let's say, a mean of 20 and a standard deviation of 4 for the first distribution. And then for the second one, same thing, but a mean of 30. And the third one is going to just be a mean of 35. So they all have the same standard deviation here. So that just gives us a list of numbers. In our data variable, put cbind, and that's going to be our first column right there. So let's put that as our first column. Now the second thing we want to do is we want to add the levels or identities of the levels. So what I just did is the first 50 is the first level, second 50 is the second level, third 50 is the third level. Great. So let's put that in. Basically we're going to use the rep function to put 1 to 3 50 different times, but this isn't quite what we're looking for because what we see, it goes 1, 2, 3, 1, 2, 3, and so forth. What we want is 51s, 52s, and 53s. So I could just put this sort, so it's going to sort it in ascending order here, and then what that gives us is our first 50 is 1, second is 2, and so forth. So that's going to be our second column here. So let's put that into our cbind. And then we also want to add participant IDs here. So this is something that really is going to matter for the function we use later. And so the way we're going to do this is each person, because this is independent samples, so we're going to have 150 different people. So we could just go 1 to 150, and that's going to give us 1 to 150. And that's going to be our third column here. Perfect. Now, if I do that, I get data, which has our scores, our levels, or the identifiers of our levels, and then finally our participant IDs. So it's always good to plot our data, so we can actually put our second column, which is our variable identifiers, as our x variable here, and then our first column as our scores, which is our y variable. Now if we do that, what we see is this scatter plot, so we have individual points for each level. And you can see this one's about 20-ish, for the mean, this one's about 30, and that one's about 35. Great. So how do we do a ANOVA to see if these are significantly different or not? Now it takes a couple of extra steps up here. So what we actually want to first do is turn our data variable into a data frame. So as.data.frame data. So we're just repopulating our variable as a data frame. The next thing is let's name these columns. So I'm going to put column names data equals C. The first one I'm going to just put scores, and the second one I'm going to put levels, and the third one I'll put subjects or subject. Now with your data you should be a lot more descriptive than this, but I'm just rushing through this and that's okay. The last thing we want to do before we can actually run an ANOVA is we want to tell this ANOVA what are these. And so we have everything as a numerator right now, but that's not true. Our levels, for example, is actually a factor, and so is our subject. So what we want to do is our second column is actually going to be a factor, so we could put as.factor data 2, and then we want to do the same thing for our third variable 2, which is our subject's variable. And then what we'll see is that these are now identified as factors. So what's next? We're going to use the easy ANOVA function from the easy package. So let's run that. And then we're going to have our ANOVA results equals easy ANOVA. And this function, it works really well, but it's not entirely intuitive. So the first thing it does is it wants a parameter dv, which is our dependent variable. But then we have to put equals dot brackets, and then we're going to put the scores title here. Then we're going to use comma, and then we're going to have between, because we have a independent samples design, equals dot brackets and we're going to put levels here. And then finally what we need is WID, which is our participant IDs, which is actually subject here. And that's this one here. Now we're going to add a couple other things. So first off, we want a detailed output. So detailed equals true, it just gives us a little bit more information. We want type equals 3, and this is just the sums of squared we're using. If you don't know what that means, look into it. It's an important factor. And then we want to tell it what data variable are we looking at, and that's our data here. So this is our variable name here. I do this in all my videos, but really I should name this something better so I don't put data equals data all the time, but you get the point. Now if we run this, we get our ANOVA results here, and there you go. If you look at our Levene's test of homogeneity of variance at the bottom here, because it's significant, we actually violated our homogeneity of variance, which is funny because we actually put them all as a standard deviation of 4, but it is random sampling, so it is possible, and that's what happened. So let's go through the interpretation here. And what we have here is our intercept, but we can ignore that for now. And then we have our results down here. So we have levels with a degree of freedom for our numerator of 2, which makes sense because we have 3 levels, which is k, and then is k minus 1 is our degrees of freedom. And then our degrees of freedom denominator is 147, which is our n of 150 minus our k of 3, so 147 makes sense as well. We have our standard deviations of the numerator and the denominator. We have our f value here, and then we have our p value here. So it's very much significant. And finally, we have our generalized eta squared. So we can write that out as the following. So f, we want our 2, 147 from here equals our f value of 140.41. P is really small here, so we can just put is less than 0.0001. And then generalized eta squared, usually use the eta value, but I'll just put GES equals 0.66 here. And there you go. There's our results.